Hello? Hello? Oh, wait.
Hi.
Oh, okay. Hello. Can everyone hear me? If someone else answers in the affirmative, that'd be great.
Yep.
Okay, excellent. Well, hi everyone. It's interesting times, I guess, we're living in right now, so it's good that we have this technology that can help us carry on. I think that this course, as I said in my email, won't be totally affected in that so much of it is sort of, I guess, tutorials followed by self-directed review of the videos, so I actually don't think it'll be that bad. Um, that being said, we're going to try to make this as interactive as possible. There is going to be some, I guess, reformatting of the overall course. I'll just open the syllabus here. Namely, in that in the final part of the course, you can see there's a week of self-directed research. And essentially, what I had planned for is that you guys would sort of go into the wild, figure out how to use an advanced grasshopper technique or plugin by yourself, and then I would sort of walk around and I would kind of walk around and sort of help you guys work through your projects. That's worked successfully in the past. So we will. Oh, some people are having a problem with the audio. Is that better? Can you guys hear me? Can no one hear me? Okay. Test, test, test. It looks like it's happening on my end. Okay. So, for those of you who are having issues with the audio, I think you need to check on your end. That being said, those... Here. Maybe I should type this then, just for those who can't. For those of you who can't hear me, check your settings. It seems fine. Okay. So I'll just keep going and so I'm just going to type that message. Okay, so as I was saying, essentially we need to figure out a way to do this sort of last week of self-directed research, and I'm going to work on that for next class, and I'll sort of let you guys know what I'm thinking. I still want to incorporate this self-directed research because I do think it's an important part of learning Grasshopper, and will sort of give you a solid foundation for moving forward in your Grasshopper work when you're done this course. But the parameters might be slightly changed, so I'll just sort of let you know what's going on with that. Before I jump into assignment 1, I want to maybe set up, so sorry about this infinite loop you can see here, but I want to sort of talk about how we're going to use this program, collaborate to work in the class. So for the most part, I'm just going to share the screen. You're going to, watch. But if you do have questions, Zara is going to be monitoring the chat. So what you can do is just type something in the chat bar. So the chat bar is this collaborate panel right here, the bottom right-hand corner. Just open it up and you can see people are already typing. I'm not going to be actively watching this because I'll be actively working in Grasshopper. But if you do have something, Zara will pick up on it, and then she'll let me know, and then I can sort of address that. So it's just to give me a heads up. And outside of that, if there is anything that's really not working for you, send me an email and I'll get back to you afterwards. I'm still going to be posting all these videos on YouTube, so the same YouTube address is where all these videos will be archived. The final thing is before we had done a kind of two-part method for each class, wherein the first part was me lecturing for a little bit, and then the second part was you guys reviewing a video, which I'd pre-recorded. Since it seems kind of less effective for me to kind of record a video and then just tell you, okay, watch it. It's kind of the same as if you watch the video or if I just record it live. So that's what I'm going to do from now on. I'm going to record live. It will go a max 2 hours. Some courses might go a little bit shorter, an hour and a half or so. It really depends. But I will try not to go over 2 hours because that's pretty long as it is. So I guess I always say any questions there. If you have any questions, type them, and then Zara will read. She'll speak them out to me. So beyond that, I just want to go over our assignment 3. Oh, is this a question coming through, or is this... So the one thing I would say is, for everyone, if you'd be able to mute your microphone, if you're not actively asking a question, just so we don't get any feedback. And right now I'm kind of hearing some static. I think it'd be best if Zara is kind of the only one who can sort of share audio, sort of speak for the group. So let's cover assignment 3. So assignment 3 is due at the end of the course. There's a slightly modified hand-in date since we won't be presenting them to the class. I will compile them in a folder so all of you will be able to see each other's work. I think that's an important thing. And of course, I'll give you kind of more elaborated feedback for the assignment 3, but I'll email that to you. So the third part of our project is a parametric viewing tower. Now, I'll just skip to the end to some precedents I put here. And the reason why I included precedents is not so much that I formally want you to, reproduce any of these in particular. Some of these, might not even be best modeled in Grasshopper, but more so as kind of an idea of what you could possibly do, and also to just familiarize yourself with the viewing tower typology, because it's a less common type, but I think it sort of affords some interesting opportunities, so you don't have to deal with things like rooms, windows, if you don't want to. So it can be an exterior space or an interior space. So we're going to be designing one of these to sort of cap off this project. So there are, of course, some requirements. So using any Grasshopper techniques covered in class and any you might explore on your own, develop a parametric viewing tower. So, and then we have these requirements here. So your tower must be at least 3 stories tall and have stairs and or ramps connecting all the levels. So there's no height restriction, but at the very least, you want to have 9.5 feet at very, very minimum from, floor to ceiling probably. So just make sure people can fit in your tower, and then stairs and ramps, make sure all your levables are accessible. So there are no size restrictions on your tower, but must sit comfortably in the site and accommodate an average of at least 5 patrons per level. So when I say average, what I mean is that if you wanted to, you could always, no, I don't have my drawing computer. I'll open Paint. You could always have a tower, that is kind of like a pyramid. So the levels sort of go up or get smaller as they go up. So, on this level, you could have room for, a whole bunch of people. This level, a few less people. And maybe at the top, you just want to have this one little lookout point for one person. That's fine. It's just the average for all levels needs to be 5. So if you have 3 levels, you need to accommodate 15 people. So that's what that means. your tower must be directed towards a view of your choosing. What I mean by this is, of course, we have the North Shore Mountains, but we also have the cool shipping docks to the west of this site. We have a bridge directly to the east. Maybe you want to be subversive or something and turn the view back on downtown itself. Regardless, I just want you to be considerate of what your viewing tower is actually viewing. And it doesn't have to be unidirectional in that it doesn't have to be enclosed on one side and really focused on one. But I do want you to think about what you're doing and not just have a tower, you know? Your tower must be located in the future park portion of the site, so that's right here. And this is kind of the big one, so you must incorporate a grasshopper technique / plugin not shown in class, or greatly expand upon a technique / plugin shown in class. So please confirm with me no later than March 23rd as to what your goals are. So what I mean by this is that for this final assignment, sort of the impetus will be on you in that you need to go to Food for Rhino. Just bringing it up. So you need to go to Food for Rhino, for instance. Okay. Food for Rhino, for instance, and download one of these Grasshopper apps. So there's a lot in here. Sort of go through them, see what interests you. It could be an analysis tool that you use to drive a form. It could be something that, you know, deals with terrain perhaps and incorporates it to your tower. It could be like a remeshing tool. There's a lot of things in here. And essentially, you know, I want you to go through and sort of see what piques your interest. Let me know, and then I will kind of help you through that as much as I can over email. Now, if we cover a technique / plugins shown in class, in particular, we're going to cover a plugin called Wasp that I think is pretty cool. And if you're like, this is what I want to do, that's fine, but you need to greatly expand upon what I've shown in class. You can't just redo what we've done in class. So the idea here is that you can sort of self-direct your research in Grasshopper to sort of further your own learning after this course. So part 2 is, apart from the viewing tower, please revisit your entire project and make tweaks to the parks. Could be small or large, depending on how much you've developed them. And please ensure that your park has an overall unity. So essentially, we want to consider assignments 1, 2, and 3 as one kind of big project, right? So the goal of this course is not only to teach you Grasshopper, but also to leave you with a good portfolio project that would work not only for, hey, give me a parametric job, but also would sort of just look great in either a landscape architecture or architecture portfolio. So just take care to sort of clean everything up and, you know, work on something that you'd want to put in your portfolio. So it looks like a few people are still having trouble with the sound. I'm not really sure what we can do. I think just, again, for those of you who are, I am recording this, so review after, and hopefully we can kind of figure this out afterwards. So there definitely will be a few growing pains here. So for the assignment 2 or assignment 3 deliverables, again, there's 2 major components. So one is the Grasshopper file, you know, multiple or singular, and a reduced Rhino file for the viewing tower. So make sure your Grasshopper files are well organized and annotated. And I just wanted to say right now that it almost brought a tear to my eye, how well organized and annotated all of your files were. Just in general, everyone did a great job at that. So I really, really appreciate that, and keep that up. Like, everyone got full marks for that. Literally everyone. It was so great to see. So just keep that up. And of course a reduced Rhino file, sort of pared down to the bare minimum needed to run your Grasshopper script. And then one final drawing, again, the same kind of format, 24 by 36. If you feel like you want to fit more stuff on your sheet, you can go larger. Maybe I'll revise this assignment 3 to say at least 24 by 36, but, you know, whatever you need to fit everything on there. Of course, does not need to be printed out. And it must include at least one rendered Axo site drawing, one section/elevation of your viewing tower, at least one plan of your viewing tower, at least one rendered perspective view of your tower, and at least one perspective view taken from somewhere else in your park. Please label your drawing. So I'd like to see kind of section markers, north arrows, and still label your streets. So for all of you, I know I commented on that for some of your assignments, so please include those. And again, please consider this a presentation board, not a set of technical or construction drawings. A lot of you did do line drawings, which look great, and no one was sort of going into construction drawings. So I think no one's projects jumped out at me as being too technical, so everything was good. So your files are due Monday, March 30th, and I've revised the hand-in time to 10 p.m. Because, of course, we won't be presenting them. I won't be marking them before then anyways. So I thought rather than a presentation, I can just schedule this time to sort of, you know, help anyone, like any questions. I'll just sort of leave my schedule open so people can join, collaborate, and ask questions if need be. So due Monday, March 30th at 10 p.m. I'll email out a Dropbox link later this week and the same file naming convention. So I guess, does anyone have any questions right now? I guess if there's anything in the chat that Zara can bring up, or if anyone wants to kind of chime in, let me know. Okay, so without any further ado, we are going to jump into Rhino. So in the Dropbox folder, you're going to see 200316 Solar Facades, and we're going to open that Rhino 3D model. Okay, so what I have here is essentially a base form and then two kind of parametric facades. Now, what I've based these on is if we go to the last, actually it was the first 200309 parametric facades. I have these examples in here. And the two examples I was sort of considering here was this Acme Eastland Tower Center. So this one right here, I want to do something like this based on solar vectors. So that's what this is. This is kind of a stand-in for this, and using the techniques shown in this methodology, you'll be able to accomplish something like this. Furthermore, I kind of like these rotating brick facades that seem to more directly respond to solar angles, as well as these morphosis panels. They sort of respond to a more, I guess, technical and sophisticated way of understanding solar vectors. So that's what this one represents here. Even though it might look, you know, a little bit simpler in form, all these louvers are sort of nicely configured to respond to, on this case, I guess it would be east sun, north sun, or south sun, west sun, and you can see in the back right here, north sun, they're totally horizontal. So essentially we're going to use our solar kind of calculation method we briefly covered last class, and we're going to end up with these kind of facades. So what I'm going to do is I'm going to open Grasshopper. Now, when you open Grasshopper, I'd like you to open the Grasshopper file in Solar or in today's date. I am going to open a different Grasshopper file just because it has my notes. All right, so what I want to start out with is sort of just remembering where we ended at the end of last class. So you can see what I've done here is we have our solar calculator, the first part, which just gives us the moments. And for this, I'm just looking at April 1st, and I'm going between a certain time. I think your time might be different in your file. And the time in your file is based on the sunrise and sunset. And I've just copied this panel right here as kind of a reference. So what this is just the sunrise, sunset in a particular month. So if you are doing these solar analyses for a certain date, all you have to do is figure out when the sunrise is, when the sunset is, and enter it into approximately the sunrise, sunset to the nearest hour. And again, we have the sample time every 30 minutes, and these suns here represent the solar angles at these times on this specific date. From there, we create the solar vectors, and these solar vectors are used to, one, give us these nice, beautiful, sunny-looking suns, and two, to do an analysis on the actual geometry. Now, this is the thing we covered in class on last Wednesday, but just to refresh, what you can do is you can select this kind of twisted shape here, maybe move it more towards the origin, doesn't matter though. You can right-click the geometry to analyze, set one BREP. You can hide this, and you can see what's happening is it's giving you a preview of the solar irradiation of this object based on these positions in the sky, so these different times on a given date. If you want to see your moments analyzed, it's just right here. And if you want to see sort of your legend, it's right here. So essentially what this means is that on a half-hour basis between these times, maybe it's easier, more intuitive to set it to every 60 minutes. So on an hour basis between 7 and in this case 2 p.m., areas that are in red, they receive sunlight for the full 8 hours, and areas in dark blue like this receive sunlight, direct sunlight that is, for 0 hours. So that's what this analysis means. In this kind of definition, if you want to add some context, you could simply, for instance, draw some sort of rectangular prism like this, or multiple rectangular prisms. You can just select it in this secondary BREP. Might want to rename it to context BREPs. But you can select this, right-click the context BREPs, go set one BREP, and then you can see that that does indeed affect the shading. So if I make this bigger, you can see that this is actually getting shaded. So this tool, as it stands right here, is kind of just a nice little tool for you guys to use. You can use in your studio, and it's a good and most importantly accurate way to do a solar analysis. So if you have any more questions about this, how this works, refer to last class's video, and or else just send me an email. I'm more than happy to help you with this. And this vector component here can be used as the basis for so much more. So that's what we're going to get into this class. So what I'm going to do is I'm just going to select this second part of last class's definition. So everything behind the sun preview, we want to leave that on because it's kind of nice to see where our suns are. So I'm going to select all these other groups, and then I'm going to right click outside them and go to disable. Oh, and just in case someone didn't notice in the comments, it looks like Megan has switched to Chrome from whichever browser she was using before, and now her sound is working. So for those of you, who aren't hearing sound, try switching browsers. It seems like that works. So what we're going to do is we are going to start by making a shape in Rhino. So I'm just going to delete this stuff here. I'm just going to show you how I made this twisted shape. So what I did was I just went into the polygon tool right here. So you can click polygon or type polygon. Number of sides doesn't really matter. And I'm just going to click somewhere in the center and draw a pentagon, like so. As usual, I'm not really caring about units in this, but of course be conscious of your units when you're actually designing your assignment 3. Once I have this, now what I'm going to do is just go solid, extrude planar curve straight, like so. Now, if you're catching up, you can just use the twisted polygon that was already in the saved Rhino file, so you can use that to work through this video with me. Once you have this, to twist something in Rhino, it's quite easy. You just go to Transform, Twist, and then you define an axis. So it could either be the center point. You could twist around the center. Maybe I'll try doing that. So I'll just find the midpoint here. And I have Smart Track on, so down here you can see Smart Track. And I'm just essentially finding the midpoints, so 3 points like that, and finding the intersection. So that's how I'm finding the midpoint of this kind of pentagonal polygon. And then once that's set, I'm just going to twist it like so. So the only reason why I'm doing this is it's kind of an interesting shape, and I want to show you that we can use this on something more than just a regular rectangular polygon. So again, we've disabled all of this stuff here. What you might want to do is maybe save as your file. So just save it. And just for sake of keeping the canvas clear, maybe you just want to delete that. That's what I'm going to do, just so I have some spare space there. I'm going to refer to my notes for just 1 second. Okay, and so what we're going to do is we're going to start from these vectors. Now, if we look at these examples here, so this Morphosis building here, or maybe more directly related, this Acme town center here, I'm assuming that they don't have the same kind of parametric facade on the roof, and for sure I know that they don't have the same facade on the ground plane. So what we're first going to do in our Grasshopper file is I am going to separate the sides of this shape from the top and the bottom. So to do so, first I need to reference this object. I'm going to go to params, geometry, brep. I'm going to select this twisted polygon I've made. I'm going to right click my brep. I'm going to go set one brep. I'm going to right click this component, and then now I will name this input geometry. And I'm just also going to close my window a bit because it's freezing in my room. Okay, so all good now. So this brep has been referenced. And now what we're going to do is we're going to divide the sides from the top and bottom. This is usually where I'd ask a kind of question like, who can figure out what we could test for to divide the sides and top? And I mean, unless anyone answers within 2 seconds, I'll explain it. I am going to take a sip of coffee. Okay, so simply put, the way we're going to separate the sides from the top and bottom is we are going to figure out the normal vectors of each surface. Now remember, the normal vector is the vector that's perpendicular to a surface. So for example, if we have a rectangle like that as a rectangle with an x-axis and a y-axis, the normal vector is something perpendicular to both of those that goes straight up. In this case, if this is x and y, goes straight up in the z direction. So to do that, to analyze each of these surfaces by themselves, first we need to explode this BREP. So we'll go to Surface, Analysis, Deconstruct BREP. We'll take our input geometry, plug it into Deconstruct BREP. And then now you can see in our faces, we have 7 faces of the BREP. So it refers to the 5 sides of our pentagon, top, bottom. And now for each of these faces, we're going to figure out the surface normal. So we can just simply, to do that, go to Surface, Analysis, Evaluate Surface. So Surface, Analysis, Evaluate Surface. Plug our faces of the BREP into our surface input. And now what we want to do is we want to right click on our surface input and go reparameterize. So reparameterize. And again, the reason why we want to do that is in Rhino, on a twisted surface, you know, it has a U coordinate along one edge and a V coordinate along the other edge that follows the twist. By default, this might be 1 to 1,000. This might be 2 to 777. It's kind of random. When you reparameterize, it sets U to be 0 to 1, V to 0 to 1. So that's what we're doing when we reparameterize. And the reason why we want to do that is we're going to right click on our UV input. We're going to go to set one point. In Rhino, make sure that your type equals coordinate. So if it doesn't, just click right here, set to coordinate. And then the point location we're going to type is 0.5, comma 0.5. And now you can see we have all these planes on the middle of the surface. So if we think of each surface as having a U of 0 to 1 and a V of 0 to 1, then it makes sense that if we analyze the surface at 0.5, 0.5, it gives us the center of the surface. Now, what we're going to do is we're going to deconstruct these normal vectors to get their component X, Y, Z components. So what we'll do, Andrea, do you have a question? Yes, I can do that again. So essentially what we're going to do, if you have a question, I think that, how do you raise your hand? If you figure out how to raise your hand, I guess it's this little raise hand button right at the bottom of your screen. That works quite well. It sort of gives me a loud notice, so that works well. So I'm going to sort of just review what I just did there. So I have my input geometry. I put it into deconstruct BREP. So that is right there. So under surface analysis, deconstruct BREP. And I plug that into the evaluate surface component. So that's under surface analysis and then evaluate surface. And what I did was I took the faces, plugged into the surface. I right-clicked the surface input, went to reparameterize, again saying our UVs from 0 to 1, 0 to 1 there. And then the UV, I right-clicked the UV input, I went to set one point, and I just typed 0.5, comma 0.5, which selects the center point of all these surfaces. So now we have our normal vectors, and these normal vectors are the z-axes of these planes. So you can think about the z-axis on this one will be straight up, z-axis on this one will be straight down, and these z-axes will be kind of somewhere in between. So that's how we're going to test which surface is the top, which is the bottom, which are the sides. So to do that, we'll go to vector, vector, deconstruct vector. We'll take our normal and plug it into the vector input. And now we can see here, we don't have to worry about our x and y, but if we look at our z, you can see that we have 4 or 5 that are more or less 0, because, you know, all these are more or less horizontal. But then at the end, we have a -1 and 1. So we can assume that -1 corresponds to the bottom, -1 corresponds to the top. But what we're going to do to make the top and the bottom the same is we're going to use the absolute function. So we're going to go to math, operators, absolute. We're going to take our z values, plug them into absolute. And now you can see that all of these are positive, so absolute just takes any value and turns it into a positive number. And now you can see we have a bunch of things that are close to 0 or 0, but then we also have 2 1s. So then what we can do now is we can test these values, say, hey, if you're 1, then you're the top or the bottom. So to do that, we're going to go to math, operators, equality. And what we're going to do is we're going to take our absolute value. I'm just going to move this over so I have more grasshopper real estate. I'm going to take my absolute value. I'm going to plug into A. And then B, we want to test it if this absolute equals 1. So what I'll do is I'll go to params, primitive, integer. I'll right-click this integer. I'll call it 1. So this is the name, not the value. But just for, you know, returning back this definition, I'll call it 1. I'll go to set integer, and I'll type 1, so numeric 1. And then click commit changes. I'll take this 1, and I'll plug it into B. So now you can see if we hover over the equal sign, essentially what we have is a bunch of falses. So the sides do not equal 1. Their normal vector's z value is not 1, aka it's not vertical. And then the last two are true, which means that the z value of the normal vectors of the top and the bottom are vertical. So that's how you can differentiate between a flat roof and ground from the sides of an object. So since we've done that, we just need to split these up into 2 different lists. So to do so, we can go to sets, list, and then dispatch. The list that we want to filter will be our faces. So go to your deconstruct brep faces. The F output faces goes into L, the list input. And then the dispatch, what it does is it dispatches these items into 2 lists based on a pattern. So list A will represent the true values, list B will represent the false values. By default, your pattern's true, false, but what we can do is we can take this equal output and plug it into the pattern. And now what you'll see is that list A has 2 surfaces. They'll be the top and bottom. And list B will be all our side surfaces. So that's what we're going to do. We're going to sort of work with our side surfaces now. I'm just going to disconnect all from this so I don't have those wires in our way. So what we can do now is, just for future reference, we can go to params, geometry, surface. Again, we'll need 2 of these, so params, geometry, surface. We'll plug our A into the first surface, our B into the second surface. And if I select A, you can see that it's selecting the top and the bottom. So I can just right click this component, call it top, bottom. These ones, when I select my surface component there, it's selecting all the side surfaces, so I know that's correct. So I'll just right click this and call this side surfaces. It doesn't matter if your side surfaces and top and bottom surfaces are in the opposite order. What matters is that they're in two separate lists. So what we can do now is we can preview off all of this stuff except for our top, bottom surfaces and side surfaces. You might want to hide your base geometry in Rhino itself. So I'll go Control H. And then what we can do now is I think this is a good time to group all of this stuff. And then we can call this group separating out top and bottom surfaces. And of course, in assignment 2, in assignment 3, as you all did very, very well in assignment 2 and 1, add notes. So notes go here explaining what you've done. I'm just going to plug my solar vectors back into my little sun preview component there just so we can see the suns. Okay, if anyone has any questions, click the little raise hand button. If not, I'll go on to the next step. I'll just zoom here for a second. All right. So what we're going to do now is, again, if we think back to this kind of shape here, what we're going to do is we need to essentially figure out for the center of each of these oculi, these openings, how much solar radiation does it get? And once we figure that out, we can use those values to determine how large the opening needs to be. So first, we need to figure out where we're sampling. We're going to be working with our side surfaces here. So for now, we can just kind of ignore our top and bottom surfaces. Just referring to my notes. Okay. So what we're going to do is, before we sort of do anything else to make life easier for us, what we're going to do is we're going to right click the side surfaces and we're going to click reparameterize. And again, that just changes their UVs from 0 to 1. 0 to 1. It's just a good habit to get into reparameterization whenever you can, just because it sort of creates a constant UV range. And then what we're going to do is we're going to divide this surface. So we're going to go to Maths, Domain, divide domain squared. So divide domain squared, I believe we've used this before, but it just divides a domain, a 2D domain, into segments. It also can divide a surface into segments. So let's take our side surfaces, plug into the I input. And then also, let's take two sliders and plug them into the U input and the V input. So I'm going to double click on the canvas. I'm going to go to 1 less than, I'll say, 30. I'll click enter. And what I'm going to do is I'm just going to copy this slider. So Control C, Control V. I'll plug that into U, plug that into V. And I'm not going to label these right now because I'm just going to wait and see how this surface is actually being divided to figure out what is horizontal and what's vertical. I'm assuming that the U direction is horizontal, but sometimes it flips on you. So we're just going to wait for a moment. But since we have that, what we can do is we can create boxes on these surfaces. So we can go to Surface, we'll go to Transform, Morph, Box Morph, Transform, Morph, Surface Box. We'll take the divide domain output. plug it into the surface domain input. So we'll take divide surface output, plug into the D input. Now the surfaces are going to be our side surfaces. Now this wire here is grafted. We know that because it's dashed. And if we hover over the surface output, you can see that we have 5 different branches, or 5 different boxes, as we're kind of thinking about them in this class. You can also see that there's leading zeros, so 0, 0, 0, 0, 0, 1, 0, 0, 2. And again, if we think about that, what that means is that 0, you can think of as an outside box, 0, a second outside box, and then we have our 5 boxes inside of these boxes, which contain our actual surfaces. So these outside boxes are superfluous. We don't really need them. So to get rid of them but still be able to analyze these surfaces in isolation, what we'll do is we'll right click our segments output and click simplify. So now you can see there's no leading zeros. Now, in the same way I like reparameterizing, I like simplifying because it just helps us, better think about what our geometry is going to do. So since this is grafted and our side surfaces are not grafted, we know that we want to essentially match this data. So the way we match this data is we graft the input of the surfaces. So I'm going to right click S and click graft. And then I'm going to take the side surfaces and I'm going to plug into the S input, so the surface input. You can see here, if I hover over the surface input, that again we have leading zeros. What I want to do is I want to right click on that S input and click simplify. So now if we hover over it, our data is organized in 5 branches, 0, 1, 2, 3, 4. And our domain divisions are also organized in 5 branches, so 1, 2, 3, 4. So that's what you want to see. You just want to see matching data structures like that. Now we can address our U and V count. So right now mine are 1. So I have just, 5 singular boxes. If I increase U, you can see it's increasing the boxes in the horizontal direction. So what I can do is I can right click my U count slider and I'll call this horizontal segments. V, if we increase this, you can see it's indeed increasing our boxes in the vertical domain. So I can right click the V count and change that to vertical segments. And then the final thing we have here is our box height, which essentially is how far off these 3-dimensional boxes project from our base surface. We're going to grab a slider so we can change that value, because by default it's 1. So I'll double click on the canvas. I'll make a slider that goes from 1.00 less than, and I'll say 10.00 and click enter. I'll plug that into H. I'll right click this and call it box height. And now you can see as we slide this in and out, these boxes get thicker. So this is going to increase or decrease the thickness, the depth of our facade. So now that we've done this, we can group these components here. And this group, I'll right click on it and I'll call it surface boxes. So the next thing we're going to do is we have these boxes and we want to analyze the solar irradiation at each point on these boxes. So what we're going to do is we are going to find the center point of the box, find the point on the surface, our base surface is closest to that center point of the box, and then use that to calculate the solar irradiation. So we're calculating how much sunlight the inside of this building gets from the sun. So to find the center point of the box, we go to Surface, Analysis, Box Properties. We take our surface box, we plug into Box Properties, and now you can see it's going to give us all our center points. So that is the C output right there. And then what we're going to do is we're going to go to Surface, Analysis, and then Surface Closest Point. Our points, so P input is the sample point. Our center point of boxes will go into P. And our base surfaces will be our side surfaces. Now, again, since these side surfaces are not grafted, we don't want to compare, 144 times 5 times 5 closest points. So we want to make sure the data matches up. So we have 5 branches here of 0, 1, 2, 3, 4, 5. We have 5 surfaces here. And if we remember what we did here to get 0, 1, 2, 3, 4 in terms of branches, is we right-clicked, we click graft. So on the base surface input on surface closest point, I right-click, click graft. And then I'm going to right-click again and go simplify. And then I'm going to take my side surfaces and I'm going to plug into the surface input. So if we hover over the surface input, you can see our branches. There's 0, 1, 2, 3, 4. And our points are organized by those surfaces still. So 0, 1, 2, 3, 4. So now we know that we are getting the right data match that we want. And now you can see if we select our surface closest point, we simply have these points on our base surface that are closest to these center points of the box. So what we're going to do now is we are going to analyze the solar vectors based on these points. And if you remember what we did last class, let's do that. So last class what we did is, oh, that's not what I want. Sorry, I'm not a Microsoft Paint Pro. Okay, there we go. I think this is the right thing. So yes, last class we had a sun, like that. And this sun, it had solar vectors. So we can say like that. Now, if our surface looks like this, so this twisty surface, maybe let's make it twist more like that. So we're building a question mark building, I guess. Essentially what we want to do is for each point we're analyzing on this building. So let's say we're analyzing these points. What we want to do is we want to take this solar vector, but invert it. So it's the direct opposite of this solar vector. And then what that will allow us to do is to take this vector and say, is this vector intersecting with the either context? So we could, let's say, have a little other building there. And if it's intersecting with the context, then we know that point's in shade. Or if the point is intersecting with the same building we're analyzing, so like this point here, we also know this building's in shade. So that's sort of the basics of how we're going to do this analysis. So we know that any point that doesn't intersect with either context or the building itself is receiving sunlight at that given moment in time. So that's kind of the algorithm behind our solar analysis. So what I'm going to do now is I'm just going to preview off this box properties component. just so we see the surface closest point. And what I'm going to do, maybe I'll also preview off the surface boxes for right now, just so we can see this. What I might also do is decrease the horizontal segments and the vertical segments. Again, just so we get a better view of what's going on. And then we'll start drawing those inverse vectors from the sun. Now, what we want to do is we want to analyze each of these points by themselves. So we don't really care about what face they're on anymore. So to do that, what we're going to do is we're just going to take these points, so the P output, and we're going to flatten it. So now we've gone from having 5 lists, so one list corresponding to each side, to just one list. So they're still in the same order, it's just they're all in the same list. So we've lost the information of what side they're on, but it doesn't really matter for us. So from here, what we're going to do is we're going to draw some lines from them representing these solar vectors. So we're going to go to curve, primitive, line, SDL. We're going to take our points and plug into S. So S stands for line start point. So you can see by default what's happening is all of the lines they're drawing in one direction. Maybe now's a good time to change our length. So we can right click the line length input, go to set number, and then set something that will for sure intersect. So I'll type 1000. So now you can see I have all these lines. They're all drawing straight up. But I don't want to test a straight up sun. What I want to test is our solar vectors. So if you go back to the solar vectors part of the component, so this is in the class file that we started with. If you take the vectors output of the solar vectors component, take that output and plug into the line direction input. And now you can see that we've changed the direction of the lines. So you can also see that our lines are kind of skewed. And the reason why this is happening is because these points are in one list. All these directions are in one list. There's 8 directions. And what's happening here is that, does this work? First time trying this. If we, let's say, have one, oh, that's not what I want. We have 1, 2, 3, 4 lines. And then let's say we have 1, 2, 3 solar vectors. What's going to happen is vector 1, 2, 3. So vector 1 is going to match up with line 1. Vector 2 is going to match up with line 2. But then vector 3 is going to match up with all the rest. So Grasshopper will sort of work to match this data as far as it can. But once it runs out of data in one set, in this case, the vectors going into D, it's going to start matching that vector over and over again to all the remaining line or all the remaining points in the set of analysis points. So that's why we see these multiple different solar vectors a couple times, and then everything else is the same. So what we need to do is we need to right click on our graph, or right click on our start input and click graph. Furthermore, you can see we have a leading 0 there. So just for a good Grasshopper habit, we can right click on the start input and click simplify, and that gets rid of that leading 0. So now all our points are in a 0, in my case, to 89 format. And now you can see each point has all of the solar vectors. So each of these lines on each point corresponds to a solar position right there. Sorry for having to take sips of coffee quite frequently. I'm still getting over a cold. So now what we can see, though, is that if we think back to our little algorithm diagram, we needed to invert the direction of these solar vectors to test if they intersect with either the context or the building itself. So we need to inverse the direction of those vectors. So what we'll do is we'll simply, on our D input, so that's the line direction, we can right click the D input, go to expression, and just type -x. Commit changes, and now you can see all the vectors are going opposite to the sun, but they're still maintaining the same direction. They're just going in the inverse. And you can see that all the solar vectors are relating to all the points. Now the output here, you can see we have a bunch of leading zeros. Again, you can right click and go simplify. I like doing simplify a lot. It just simplifies things. So now we can group these three components here. And we can right click this group and call it, we'll just call it solar vectors applied to surface points. So this is what your definition should look like. So what we're going to do now is we're going to take these lines and we're going to test them against these different sides and tops and bottoms of the of our building here. So what we'll do is I'll preview off these lines because it doesn't really matter. What we want to do is we want to go to intersect, physical, B-rep curve. So solve intersections for a B-rep in the curve. And we're going to plug our lines into the curve input. So intersection curve, we'll take our lines output, plug into the curve's input. Now, this is kind of the first class where we're starting to get into a little bit more, I'd say, nuanced list management. Because if you think about what we want to do here, right now, these curves are organized by surface point, right? So that's why we have all these lists of 8. Because if we look at our solar vectors, we have 8 solar vectors corresponding to the hours 7, 8, 9, 10, 11, 12, 13, 14. So 7 till 2 p.m. We want to analyze each of these lines individually to test for intersections between all of this geometry and possibly some context geometry. So what we want to do then is we want to right click on the intersection curve input and go graft. So now you can see that we have leading zeros again, but then we also have 1. So you can see it goes 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. But, ooh, this is handy. But what we can do is we can still retain the order of the data. So if you look at this 0, 0 to 0, 7, what that means is we have one big container. That's the first 0, so right there. Then we have a bunch of small containers that correspond to these values: 0, 1, 2, 3, 4, 5, 6, 7. And these correspond to containers like this. So I'm not going to draw 7 containers, and maybe I will, but those correspond to those 7 containers. So even though these lines are in different lists, this outer container 0, this black one right here, still corresponds to a point on the surface. So it still retains that data. Now, if you look here, instead of having zeros all the way down, so what I've been referring to as a leading 0, these are actually meaningful. So you can see it goes 0 for the first 8 items, and then it switches to 1. So we have this 1 here. So this 1 represents the next point. But since we've grafted, now we have a bunch of smaller boxes inside of there. So someone just asked what the most recent component was, and this is under intersect, physical, and its B-rep curve. So intersect, physical, B-rep curve. I can't open it because I'm in this drawing mode. So anyways, we have our 1, which means our outer list corresponding to a point, let's say right there. And then the 8 lines shooting out from this point are these smaller boxes inside like this. So that's the way we maintain the order of this data. So afterwards, what we're going to do is once we figure out whether or not these lines intersect or not, we're going to use something called trim to get rid of the innermost boxes. And then what will happen is, I don't know if I can erase here, but what will happen is all these boxes will be erased, and then we'll just have a bunch of lines back in the box corresponding to these points. So it's a nice way of sort of keeping your data organized, but still being able to utilize the benefits of looking at objects individually. So the base B-rep now, we can plug in our top surfaces. So we'll plug in our top surfaces. You can see that we're getting some intersection points. We can hold shift, plug in our side surfaces. One thing you might want to do just in case is right click on the B-rep input and click flatten, just to make sure all of these are in one list. And then what you can see is coming out here is we have intersection points, and you can see that they have one more layer of data. So now what's happening is each layer of data, it means, so now we have 3 layers of data. So I'll just hover over this. And what's going on here now is that the first layer of data, this 0, is corresponding to our point on the surface. So 0 equals the point on the surface. The second layer of data here, so this 0, which goes down and then becomes 1 and goes all the way to 7. So that's like that. So second layer, these correspond to all the solar vectors shooting out of that point. So 0, 1, 2, 3, 4, and so on and so forth. And then when we look for the intersection between all the B-reps, all the surfaces around, this final list here, so all of these ones, so you can see it's 0 to 6. These correspond to the surface intersection points. So all the little intersections over here that are created with the sun. So those are the final smaller boxes in here. So it's kind of like those Russian nesting dolls, right? So there's all these different data points, but they are organized in a meaningful way. So that's what this means, and we'll take advantage of this. If we want to add context to our model, so let's say you have your silo on your site and you still want to analyze your tower, simply what you could do is I'll just draw a rectangular polygon right here. So I'll draw this big tower right here. What you can do is you can now select this. You can go params, geometry, B-rep to reference it. So I'll right click the B-rep, go set one B-rep with this selected. I'll right click this component and call it context. And I'll hold shift and I'll plug that into the B input as well. And now you can see that we'll have one more little box in the bottom. So this one right there. So you can see the 7, an extra one where we had 6 before. That corresponds to this new B-rep. So now we're also testing against this context as well. So now we can easily include context in our shadow analysis. So what we can do now is if we look at the points, if there's one point, then we know that that solar vector was intersected, so it means at that moment in time, something is casting a shadow on one of these analysis points. Or if there's 0 points, then it means that at that moment in time, a particular surface or context is not casting a shadow on an analysis point. So what we can do is we can use the component trim. So I'll go to sets, tree, trim tree. I'll take my points output, plug into trim tree. Now you can see that what I have here is a bunch of lists. So if I hover over this output, let's go to params input panel to see what we're getting. What this is all the points. So it's saying all the intersection points for a given analysis point. So what this means is you can see that some of these lists have 0 or have 1 point only in them, whereas some have multiple. So what this means is if one of these lists, here I'm gonna do this. So if some of these lists have, let's say, 3 points, what's happening there then is, and let's add another context building right there to make this point. So let's say we're looking at this point right here. So we're analyzing this point right here. If we think about the intersections it's going to have on its journey from this point on the original surface to the sun, it's going to have one intersection at the surface. So you'll always have one intersection at least. So this first intersection is where the inverse vector pops into life. It intersects with its original surface. It's going to have a second intersection on this small, let's say, hedge right there. And then it'll keep on going and have a third intersection there. Maybe it'll even have a fourth intersection on the backside of this building. All we know is that it's intersected more than once, so therefore it's in shadow. Whereas this right here might have one intersection, keep on going, have a second. This one might have one intersection, have a second intersection. All of these will be in shadow. Now these two up here, they'll have one intersection and then no more. It'll just keep going on into infinity. And then again here, one intersection, keep on going till it hits the sun. So what we can test is the list length, and we can say if the list length is only 1, then we know that that point is receiving sunlight. So what we'll do now is we'll go to sets, list length. We'll plug our trim data into the list length. I'll plug the length into the panel. So now you can see we have a bunch of 1s, 2s, 3s, 4s. And then what we can do is we can test, does this equal 1? Does it only intersect with its originating surface? So now we can go to maths, operators, equality. So length goes into A. We want to test if it equals 1, aka only intersects with its starting point. So we'll go to params, primitive, integer. I'll right click on the integer. I'll just call it 1 for future reference. And then I'll go to set integer, click numerical 1, and then click commit changes. And now we're going to have a bunch of trues and falses. Now, if we, again, this is why I say we're dealing with a little bit more nuanced data, or data management, that is. If we look at our little list right here, we have 0, and then we have 0, 0, and then I'll use a different color, and then 1, So, like so. And you'll notice that the first value keeps on repeating, but then it goes down, down, down all the way to 89. Again, this first value corresponds to the 89 analysis points we have on this surface. All of these, the 0 to 7 in this secondary path, so the second little box, so these little boxes in our big box that represents the point. These little boxes, they represent the solar vectors, right? So that's why there's 8 values in my case within each of these boxes. And remember, what we're doing now is before we are testing if it intersected with a specific object, but what we're doing now is we figured out this test here, right? But now what we're doing is we're increasing the amount of solar vectors. So we're going, if instead just 1, we have 2 times. Now we're considering the multiple different solar vectors, right? So what we can do is we can trim this data again, use the same trim tree component, and measure how many vectors intersect versus how many don't. And that's going to tell us how many moments each point is in sunlight or in shadow. So what we can do is we can go to Sets, Tree, Trim Tree, plug our equals into the T input. And now you can see we have 0 to 89. I'll preview off this stuff here. These 89 go back to our, or these 90 points refer back to our 90 surface points there. And if we grab a panel, so params input panel, you can see we get a bunch of trues and falses. So this first one, false, what this means is that this first point, let's say it's this one right here, is in shadow for all 7 analysis moments. So that's what the falses mean. Whereas if, let's say, find another point here, this point here, true, 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 then 4 falses. Maybe it's this one here. It means it's receiving sunlight from 4 of the 8 solar vectors. So that's what this means. Now what we can do is we can convert these trues and falses to zeros and ones very easily. We can just go to primitive, integer. We can take our trim tree, plug into the integer. Take the integer and plug into the our panel just to see again. And you can see it just takes the trues and falses, converts them to zeros and ones. 0 equals false, 1 equals true. So now we have a bunch of lists of zeros and ones. And to figure out how many moments of sunlight each point gets, we can simply add up all these zeros and ones. So we can go to math, operators, mass addition. Plug our integers into our mass addition. Take our results, so the R output. Plug in panel, see what we get. And now you can see what we get is the amount of solar hours each analysis point gets. So that's how we determine how much sun something's going to get. Now, once we've done all of that, what we can do is we can flatten this result. So I'll right-click the result and flatten it. So now all these numbers are in one list. And we'll work with this data from this point onwards to create our box mapping and our variable openings. So what I'm going to do now is I can delete this panel because I sort of don't need it anymore. We know what's going on here. I'll group all of this stuff. Maybe I'll leave my context out of the group just so we can, quickly set a new context if need be. I'll right click outside these components, go group. I'll right click this group, and I will call this group calculating the solar, I'll just call them moments, because maybe it's every half an hour, for instance. Calculating the solar moments for each analysis point. So I'll zoom in on these. And does anyone have any questions? Please electronically raise your hand if you do. Okay, great. Might I say, it feels so weird doing this, because it's like, I at least assume you guys are watching and listening, but without the human feedback and being in the same room, it's a surreal moment. But anyways, we have our results, and what we're going to do now is we're going to take these values and we're going to use them to create different openings. So what we're going to do now is we're going to go back into Rhino, and we're essentially going to start drawing these openings. So we're going to draw it in Rhino just so you have more flexibility. Maybe you don't want a diamond, you want a square. I'm going to do a little twisty thing. This will allow you to have some flexibility. So what I'm going to do is I'm just going to click on the rectangle, the rectangle command here. You could also type rectangle. And I'm just going to draw it somewhere on my Rhino screen on my XY plane. I'm going to hold shift to make sure it's a square. You don't need to, but I'm going to hold shift. So now I have this square right here. I'll just move that there. And then what I'm going to do, so we can consider this the bottom part of my mullion, so the base right there. I'm going to create the outer portion of my mullion here. So what I'm going to do is I'm just going to take this square. I have gumball enabled, so again, the little arrows coming out. If you go to the bottom of the screen, make sure gumball's on. And then I'm going to hold Alt to copy it, so you get that little plus icon. And I'm dragging it up. Okay, I see someone said the visual disappeared for them. Is anyone else having that issue? Can someone else let me know if they can still see me? Okay, so maybe, okay, so it's come back, good. So anyways, so we have this second rectangle on top of this one. And what I'm going to do is, now that it's dragged up a little bit, it doesn't matter how much it's dragged up, because actually the box height is going to determine how deep this panel is. We just want to make sure it has some depth. And what I'm going to do is I'm just going to go into my top view, and to match my twisted tower, I'm just going to rotate this rectangle. So I'll click on the little blue half arc right there, and I'll type 45. And I'll just rotate this by 45 degrees. Furthermore, I probably don't want my outer mullion to go outside of my inner mullion. Maybe you do, you can try it out. But what I'm going to do is I'm going to shrink it down so it fits within my base mullion like that. So if I click on perspective view, now what I have is something that looks like this. So I have two squares, one's a little bit above the other one and rotated 45 degrees. So now let's reference these in Grasshopper. So I'm going to go to params, geometry, curve. I'm going to grab two of these. So params, geometry, curve. I'm going to select the bottom curve. I'm going to right click on curve. I'll call it bottom curve. I'll right click this component, go set one curve. I'll select the top curve. I'll right click it. I'll call it top curve. I'll right click the top curve component, go set one curve. So now I have these two curves referenced. Now what I'm going to do in Grasshopper is I'm going to loft them. So I'm going to go to surface. Actually, not going to loft them yet. First, we want to offset this top curve based on the solar analysis. So before we project this to the surface here, we want to vary its opening, right? So essentially we're going to vary, does it open big if it's getting like north diffuse light, or does it stay small if it's getting very direct light? So in order to do that, what we're going to do is we're going to set a domain for the offset of this curve, and then we're going to offset it. So take your top curve, go to curve, utilities, offset curve. The first input is curve to offset, so that'll be our top curve. And then what we're going to do is, if your curve is offsetting to the outside like mine is, I just want you to go to your second input, offset distance, right click on it, go expression, and type -x. So now it's going inwards. And then what we're going to do is we're going to take a slider and we're going to figure out what the minimum, the maximum offset that we want is. So I'm going to double click on the canvas and I'm going to create a slider. I'm going to go 0.00 less than, and I'll say the maximum is 10.00. Click enter. And what I'll do is I'm just going to plug this slider into the distance, and then I'll slide it just to get an idea of what I'm dealing with. So you can see mine doesn't offset enough. So I can double click on my slider, edit it. Maybe I'll change the max value to 100. Doesn't really matter. We just want to make sure we can find this top value. So it looks like my top value in this case is about 42. So maybe I'll double click on my max value and I'll switch it to 45. And we'll just go like that. Doesn't matter, just for again the ballpark. So once you've figured out that, what we're going to do is we're actually going to right click on our offset distance. We're going to go to disconnect and then disconnect your slider right there. And we're going to do that because now we're going to create a domain of offsets. So what we're going to do is we're going to copy our slider. We'll take the slider that's sort of first above the second slider, however you want to organize it, and we'll call this first one minimum offset. So the minimum offset is going to refer to the biggest opening. We'll call the second slider maximum offset, and that will refer to the maximum opening, or the minimum opening, sorry. And I'll set my minimum offset to be 0. So we're going to say we're going to offset this curve from 0 units to 43 units in my case, based on the solar irradiation. To take these two values and to create a domain from them, we'll go to math, domain, construct domain. The minimum offset, I'll plug into A. The maximum offset, I'll plug into B. And now you can see it's creating that domain. So it's 0 to 43.1. So what we're going to do now is we're going to take these solar hours and we're going to remap them to enter into this domain here. So we're going to say if we have a result of, let's say, 0, meaning something's totally in shadow, then we want the maximum offset. If we have something that is a value of 8 or whatever our maximum value is, then we want the minimum offset. Or, sorry, vice versa. So what we're going to do is we are going to go to maths, domain, and then remap numbers. So math, domain, remap numbers. The values we want to remap are our mass additions. So these are the amount of sunlight hours that each point gets. So the mass addition result, plug into the values. The source domain is going to refer back to our vector count. So we want to know essentially how many suns do we have here? How many moments are we analyzing? So to do that, simply what we'll do is we'll go back to our solar vector component. We'll go to sets, list, list length. I'll take my solar vector's output, plug into list length, and it tells us how many moments we're analyzing. I'll take this length, drag it on over to our close to our remap values component, and I'll plug this list length into the source domain. So now if we hover over the source domain, it's converted this 8 to 0 to 8. So it converts it to a domain 0 to whatever you plug in. Now the target that we want to remap to is our domain right here. So 0 to 43. So what this is doing is we have a list of 0 to 8, and we're going to 0 to, in my case, 43. So for instance, let's say we have 4 from our original list, so it's received sunlight half the time. If we remap this, 4 is about halfway through 0 and 8. It's going to go to halfway between 0 and 43, so 4 would map to 21.5. If we have, let's say, 2 in our first list, that's about a quarter of the way. Quarter of a way of 0 to 43. 2 is going to remap to 10.75, for instance. So that's what remap does, just a quick review. And we can see that we have a 10.775, 5.3875, all those kind of things. So that's the remapped value. So what we can do now is we can take these remapped values and we can plug them into the offset distance. So remap values goes into offset distance, and now you can see what happens is that we have all these offsets like so. Now, what's happening here is that none of my results are actually giving me a full 8 hours in sunlight. So if you do want to adjust your offset, if you want some openings to be totally closed, you could just change your maximum offset slider. So maybe I increase my max to 60 and then dial this up until I get something that's pretty much the most. What you don't want to get is this kind of intersection where the offset's too far. So sort of dialed in to a point where it's almost closed and leave it like that. So now that we've done this, we can just simplify our output because we still want to now loft, and we want to loft each one of these curves to this bottom curve. So what we can do now is we can just simplify the output, so we get rid of all the superfluous leading zeros, and then we can go to surface, freeform, loft, and the curves we'll put in are the curves here, and essentially we can put this bottom curve in here, but I don't think it's going to work. So you can see it did work, but it only worked for one. So the reason why that's happening is if we hover over our curve input, you can see that it is going, we look at our list, our 0 list has 2 values, meaning the bottom curve and the top curve, but all the rest have 1. And that's because this bottom curve by default is in the list 0, so it's matching list 0 to list 0 here. The rest, it doesn't have an extra bottom curve to loft, so it's not doing anything. So to sort of get over this issue, what we need to do is repeat the bottom curve so it matches the amount of top curves, and then graft it. So what we can do is we can go to sets, list length, we can go to our remap values. We'll take our remap values, plug into list length, so 90. That tells us we have 90 offset curves up here. And then we can go to sets, sets, sequence, repeat data. So repeat a pattern until it reaches a certain length. The data will be the bottom curve. So plug the bottom curve into data. The length will be the list length we get from the remap values. So now you can see we've repeated this bottom curve 90 times. Since this data is grafted here, we have to graft this output data. You can see we have all these superfluous leading zeros, so we have 4 of them, so a box within a box within a box within a box within a box, which has our item. So we can right click that output, go to simplify. So now we simply just have boxes, each one containing one bottom curve. For our loft, if you still have your original bottom curve component plugged into it, you can right click, you can go disconnect, and then choose the bottom curve. So right click, disconnect, bottom curve, and then you can hold shift and drag your repeat bottom curves that have been grafted into your loft, and now you can see you get all these variable lofts. Now what we can do is we can flatten this output, because again, we want to get these all back in one list. So now what I'm going to do is all of this, it seems like a good place to group. So I'll select all these components. I'll right click outside them. I'll click group. And I'll call this creating lofts based on solar value. And I can preview off, you know, really most of this stuff. Maybe I'll leave that. So now what we need to do is we need to box map. So why don't we go back to our surface boxes group. And I'll preview back on the surface boxes. So if you remember, those are all these boxes we create on our surface here. We can control their height and whatnot. And you can see that we have 90 boxes. We have 90 lofted surfaces. So we're going to take these 90 lofted surfaces and put them in these 90 boxes. So the first thing we need to do is create a reference box. We're going to create the same reference box for each of these objects. So what we'll do is we'll simply go to surface, primitive, bounding box. We'll take our top curve, plug into the bounding box, the C input. We'll hold shift to take our bottom curve, plug into the C input. So now you can see we have 2 flat bounding boxes. And then what we're going to do is we're going to right click the bounding box component and select union box. And now you can see it creates one bounding box for the 2 objects. So this is going to be our reference box, and you can see it encompasses all of our different offsets regardless of their size. And you always want to have one reference box even if you have multiple geometries like this, because it just ensures that they're all being projected onto this surface in a similar manner. So now that we have that, we can simply do the box map. So now we can go to transform, morph, and then box morph. So we've used this one before, just morph geometry onto a box on a surface. The base geometry is going to be our lofts right there. The reference box is going to be our union box right there. The target box is going to be our surface boxes. Now, if you look at these surface boxes, they're grafted. We don't want to flatten them there because we still want them to be grafted going into our box properties. So what we're going to do before we plug this in is we'll right click on the target box input and we'll go to flatten. So that'll just ensure that the data going in is only in one list like all our lofts, and it will be matched up perfectly. So now we can take our surface box, so again that refers to all the boxes on this surface here, and take the output of that and plug it in the input of target box. And now if we preview off everything except for our end box morph, you can see what we get is kind of an interesting object whose oculuses get wider as they get less direct sunlight. So we're reducing glare quite a bit here. Now, if you want to change some of the values for these openings, you can of course go to your minimum offset, maximum offset. Maybe you say, hey, that's too wide. So you can decrease those. Maybe you find that the max or the smallest openings are, you know, too kind of puckered up on this side. So what you do is you decrease the maximum offset to make it something, so you have slightly bigger openings. So you can play around with that. Furthermore, you don't have to use this kind of you know, geometry to start with. You could always twist it more, twist it less, oh, twist it less. So there's just kind of the standard window. Or you could always just use a different geometry entirely. When you want to bake this, what you can do is you can always go to Surface, Utilities, brep join. Now you can see this is an open brep. You can right click the brep join, go to bake it on whatever layer, and now that you have in Rhino, you can offset it. So it's easier to offset in Rhino, I find, to give it some thickness. You can offset these surfaces in Grasshopper. We'll be dealing with a plugin called Weaverbird. I guess we'll probably do it next class, actually. And we'll start working with meshes, and you'll sort of be able to see how to make things look more fluid, organic, and also offset easier. But if you want to offset a brep like this, you would offset in Rhino. So select your brep, go to solid, offset. You can see it has all these crazy numbers, or all these crazy arrows. Distance, let's set the distance time, I'm going to say 5. Click enter, and it'll take a moment, but then you will give some thickness to your object. So while my computer's thinking, and we unfortunately won't have time to cover the other fins, what I'll do is perhaps post the file, so those of you who are interested, and you can sort of go into it and dissect it yourselves. If you have any questions, you can ask me, of course. But so now you can see it's offset. So now this has thickness. Looks like the offset was too thick because we have these strange little spheres at the intersections, but here's our kind of offset shape. The offset looks a little bit too clunky there, but so maybe you would offset less. So like I said, we will not have time to go over the other example I had, that kind of horizontal louver one. I will post that file in today's Dropbox folder, so if you're interested in that kind of thing, you can dissect that file by yourself, ask me questions. I don't really want to spend another class on that because I do want to get into some plugins and kind of the more wild formal stuff, I guess. But does anyone have any questions? Feel free to turn on your mic. So yeah, Emily, you can type it or ask it. Can you set multiple B reps? Yeah, okay. So can you set multiple B reps as context? Yes, you can. So all you need to do for that is go into your... I'm going to delete this join component just so my computer doesn't go much slower. You have your context here. What you can do is you can have more context, like so. And you can set multiple contexts like this. Now, the one thing I would advise against, so you just go to your context component, right click, go set multiple B reps. And that's still going to work. So you can see these openings have gone bigger because there's more shading around them. The one thing I would suggest is if your context is more complex, let's say your bridge, you probably want to make a simplified model of your bridge, if that's including your context, or those silos. Create something that's sort of on the level of made up of primitive shapes, just because that's going to speed it up. If your context contains a highly detailed, like very nuanced building which contains moldings and whatnot, it will take quite a while to analyze. So just kind of simplify your geometry to do it, but you can set as many context B reps as your computer can handle. All right. Any other questions? Okay. This video, I am going to, as soon as we're done this, I'm going to format it. And then it should be posted in a couple hours. Since I'm at home now, I can format it and post it before I leave to the office job. So yeah, I can do that. So it'll be later this afternoon. Yeah, no problem for adjusting. Today I have not trimmed my beard as per I usually do on Monday, but I'm not yet in boxers and a t-shirt, so I haven't fully adjusted to the quarantine lifestyle, so I'm glad it's working. Okay, guys. Well, unless there's something else, I'll kind of I'll just sort of stay watching the chat while I prep the video. So if there's a few other questions, feel free to type them or ask them. But with that being said, if there's anything else, just shoot me an email, and I will, I guess, e-conference with all of you on Wednesday. But I'll stick around for the next 5 or 10 minutes, just in case something comes up. So thank you.